This clip is about object-oriented design. What we're going to do today is cover the step that goes from analysis to actually designing the software. Several questions arise when you want to make this move. How can I use a model of the domain to write class diagrams? How can I make good quality requirements more explicit? What are the principles behind this process? A domain model describes in an abstract way meaningful concepts from the real world that are supposed to be modeled in software. For instance, a domain model of a student assignment submission system would describe what a student is, an assignment, a submission, a teacher, a grader, an assessment, and how these are all related. But how do you go from such a model to an actual software system? There's lots of ways you can design classes. What methods should each class define? Are they public or private? What is actually a good design? Should an assessment be a separate class, or should it be part of a submission? Are teachers and graders the same instances of a class, or are they different? Overall, a software system design aims to decompose a big problem into smaller manageable pieces. The idea behind functional design is that you give each modular part of software a single responsibility and make each module as independent as possible from the other parts. Suppose you want to create an application that reads a list of shapes from a database and then displays them. How would you design the software? Let's start by decomposing the problem into smaller independent steps. We identify 4 of them. First, locate the list of shapes in the database. Then, retrieve a list of shapes you want to display. Third, sort the list of shapes somehow, and then finally, display each shape in the list individually. So by breaking this problem into smaller subproblems, we managed to come up with the design. For some problems, this works fine. But if you chose the wrong decomposition and the requirements change, you may have a big problem. For example, maybe the database schema has changed, or can you extend the code to handle more shape types, or we need different ways to visualize or sort the shapes, and so on. You would typically split code into several methods, but if you do it in the wrong way, a single change in the requirements may have a big effect in a lot of places in the code. If we introduce a new kind of shape, we'd probably need to change code in all of the 4 steps in which we decomposed the problem earlier on. I already mentioned before that requirements can and will change for all kinds of reasons. A client may not have been clear about some point. You learn something new while implementing the system. The client changes their mind after seeing the first prototype, and so on. The functional design I introduced earlier could also be called weakly cohesive and tightly coupled. What does this mean? First, let's look at cohesion. This refers to how closely the things that a method does are related. To illustrate this, let's look at a real-world example. The Albert Heijn has low cohesion. They have everything from veggies, bread, to gift cards, alcohol, electric toothbrushes, and kitchen appliances. The cheese shop has high cohesion. What do they sell? Cheese. That's it, nothing else. But you can't beat them when it comes to cheese. Let's look at a software example. Take a look at this method. Does it have strong or weak cohesion? It has weak cohesion. This method tries to do a lot of different unrelated things. Finding examples of methods with high or strong cohesion is not that hard in Python. Take a look at the math module. The sine and cosine functions have very strong cohesion. They do one thing and one thing only. Strong cohesion is a good thing. You should try to structure your code into methods that only do one thing. Methods that are strongly cohesive are easier to maintain, understand, and reuse. If you change something in the way the sign is computed, you don't have to update any other method. Your large code base can be broken up in simple parts that are easy to understand. And finally, if a piece of code performs a very particular task, you have a higher chance that you can reuse this code somewhere else, saving you time in the future. If you want to read more about cohesion, take a look at the Code Complete book by Steve McConnell. Wikipedia also has a good section about different types of cohesion. If you find it hard to come up with a suitable name for a method, that's a sign the method has weak cohesion, especially if you lean towards giving a method a very generic, vague name such as do it, prepare stuff, step 7, and so on. Better names are get icon location, erase file, or calculate interest rate. As an example, look at some old code that you wrote, for example during your first year programming course. How cohesive are your methods? If cohesion is saying something about the inside of a method or function, coupling is about how closely different objects or functions in a program are related. Again, an example from the real world. Loose coupling is you and the person at the convenience store. You use a simple set of rules to communicate. You put what you want to buy on the counter, the other person tells you the cost, you pay the money, and you take your bag of chips with you. Each one of you could be replaced by another without disrupting the system. Tight coupling is you and your partner. There are lots of dependencies, communication rules are not clear, and it generally has a lot of effect if one of the two is replaced by someone else, especially if the person who's being replaced is not aware of this. There are different types of coupling. Data coupling means that one method relies on data produced somewhere else. If the structure of the data changes, the code needs to be updated in multiple places. Control coupling means that one method tells the other what to do, for example setting a flag to print in color or not. Global data coupling means that different methods access the same global variables. For example, every part of the code is using the same configuration data. And finally, the worst kind of coupling is pathological coupling, where one method relies on the exact implementation of another one. For example, you rely on the sign function to return the result within a microsecond, or you assume that every third field in the table is a key. If you have two methods that are tightly coupled and you change one of them, chances are you're also going to need to change the other one. If lots of methods access the database, a change in the database schema means making lots of changes in your code. If modules or methods share the same global data, it's harder to split one of them into smaller methods, because you might introduce unwanted side effects in the other method. Also, extracting such a method from the code, using it somewhere else, becomes more complicated. Functional programming enthusiasts always claim that their programs are easy to test, reason about, and reuse. This is because functional programming for a big part relies on pure functions. Functions that have no side effects and simply take input parameters and compute a result. That's why pure functions are almost always loosely coupled. You will always have some coupling, because the components of software need to communicate somehow. Passing a single parameter to a function can be considered loose coupling. But as soon as you start adding parameters or structuring these parameters and objects, coupling between the methods increases. Just like with cohesion, take a look at some old code that you wrote. What can you say about how your methods and objects are coupled? A design that's tightly coupled or weakly cohesive is considered a bad design. because a minor change can affect a lot of parts of the whole system. Functional design doesn't take this into account. If you decompose a problem in the wrong set of sub-problems of functions, all these functions may need to be changed if the input data changes. Another way to look at decomposing and structuring a bigger problem is by looking at responsibility. Let's take a look at the convenience store use case we talked about earlier. This is what the steps in the use case look like if you write them out. When you design the classes, you need to think about the responsibilities. Who computes the total value of the sales? Is it the system or is it part of the sale class? Where is pricing information stored? And how does information from a sale flow to the accounting and inventory parts of the system? Martin Fowler is a well-known software engineer who wrote several books about object-oriented design, UML, and patterns. He identifies 3 perspectives on the software development process: conceptual, specification, and implementation. In the conceptual perspective, you're purely thinking about the domain model. What main concepts are there and how are they related? In this perspective, you do not think at all about how to implement this in software. In the specification perspective, we're looking at software, but only at the interface, or how do the parts communicate, and not the specific implementation. And finally, the actual implementation perspective is the most used one, but the other 2 perspectives are equally, if not more, important. Shall in Trot map these perspectives to understand objects? In the conceptual phase, you view an object simply as a set of responsibilities. In the specification phase, you look at its methods. And in the implementation phase, you look at the actual code and the structure of the data. Object-oriented design thinks in terms of objects and responsibilities first. Here's the shape database example again, showing the 4 steps we identified. Now let's approach this in an object-oriented design fashion. First, there is a ShapeDB class with a getCollection method that's responsible for connecting to the database and retrieving the list of shapes. We have an abstract shape class with a display method that defines a generic interface for dealing with and displaying shapes. We define specific subclasses such as square and circle. We have a collection that deals with managing the list of shapes. And finally, we have a display collection method that can display shapes in a collection, and we have a sort method that can sort shapes in some order. Here's what the main program would do to use this design. First, create a ShapeDB object, ask it for the collection of shapes. Then, the collection class is responsible for sorting and displaying all shapes. And finally, each shape is responsible for drawing itself. The question is this approach robust to change? Can we add new shapes or sort them differently? The answer is yes. We can define a new subclass of shape, and we can easily change the sorting method in collection. This works because both of these changes are local to the objects that are responsible. This approach works well because we're hiding information to ensure that responsibilities are clear and exclusive. This is also called encapsulation. Shapes know nothing about the implementation of the sorting algorithm, and collection knows nothing about how individual shapes are being drawn. Given all that we've seen so far, how do we actually write a design then? Writing a good software design requires an excellent understanding of the problem domain. During analysis, you collect as much information as possible, and during design, you're supposed to come up with a solution. As we've already seen, there's not a single answer that is right or wrong. There also is no single trick that I can teach you that always yields a good design. A key question you should ask while designing software is which part of the system is responsible for what? Which class is responsible for computing the sales total? Which class is responsible for assigning submissions by students to teachers or graders? Which class is responsible for drawing shapes or sorting them? Responsibility itself is an abstract concept that can have varying levels of complexity. Being responsible for database storage is a lot more complicated than being responsible for computing taxes. Unless you live in the Netherlands, of course. Larman also identifies several principles to help design good software. These are called the GRASP principles. GRASP principles help assign responsibility to the classes in your domain model. There are 5 of them. First, we have the information expert principle and the creator principle. These 2 principles are about where the information is stored and who is responsible for creating certain objects in the system. Then we have general quality guidelines of loose coupling and strong cohesion that we already discussed in detail before. Finally, there's the controller principle that tells us which subsystems handle certain types of events or activities in the system. Let's look at the information expert principle. Who calculates the sales tax in this example? The sale, the item in the sale, or the object specifying the product? By looking at the responsibilities, it makes sense that a product specification contains the price of the product. A sales line item records the price of selling this item, and the sales should compute the total and tax. This is a good starting point to create a class diagram to specify the operations each of these classes should support. The information expert principle relates to 2 questions. What information do I need to compute something? And in which class is the information stored? In general, you should assign responsibility to the classes that already have the information. Let's look at the same example, but from a creator principle point of view. Who should create sales line items? A sales line item is part of a sale, and therefore the sale should be responsible for creating them. As a result, the sale class should probably have a make line item method. Generally speaking, if a class B conceptually contains a list of A objects, records instances of them, uses them closely, or already contains the data to initialize A instances, then B should probably be responsible for creating the instances of class A. Let's look again at loose coupling. Suppose that we have a register class with a make payment method that associates a new payment with the current sale. This is one way to do it. You call the make payment method, register creates a payment object, and then adds it to the sale. Here's another way. You call make payment, register forwards the make payment call to the sale, and the sale creates the payment. So, which one should you choose? In the left diagram, both sale and register need to know about the payment object. In the right diagram, only the sale needs to know about the payment object. Therefore, coupling in the right diagram is looser. Try to assign responsibilities in such a way that coupling remains loose. So the general principle is favor design with the loosest coupling, for reasons we've seen in several examples in this clip. Similarly, according to GRASP, we should also favor the design with stronger cohesion. So let's look at the same example, but from a cohesion point of view. The registers class main responsible is interaction with the customer. So why bother it with payment details? This means that from a cohesion point of view, this design is also better. As a rule of thumb, assign responsibilities that strengthen cohesion. Like with coupling, you can break this rule, but there needs to be a good reason for it. And finally, the controller principle states that you should assign responsibility for handling events in a system to a specific class. These are often called handlers or controllers. For example, you could have a class specific for handling mouse events, or a class that handles only payment processing events. When you start with the data you collected during the analysis, you can create realizations of the different use cases you constructed. This gives you an idea of how the classes you designed interact in each of these cases. Use the GRASP principles to guide you in creating your design. Let's briefly look at another case study, a point of sale system. Here's a fragment of a use case. Who's responsible for creating the sale object? And what other data should be initialized? The cashier is the main responsible for creating a new sale in the system. If you apply the controller principle, this means that a register should handle such request and provide a method to make a new sale. When a sale is created, the sale should initialize a list of sale line items according to the creator principle. Let's look at the use case again. Who is responsible for computing the total? In order to compute the total, you need to know the items and quantities. This information is in the sale object. If we apply the information expert principle, this means that the sale class should have a method that computes the total. If computing the total price becomes more complicated, for example, if you need to compute tax in different countries, you can extend the design so that there is a separate tax calculator controller that is responsible for that part. But that also makes the sale class slightly more complicated. To every choice, there are pros and cons. And good design is about balancing these. If you want to read more about how to go from a use case to a design, read chapter 17 of Larman's book. You can use the use cases to check whether your design is solving the problem. Does every class have the right information to perform the task? For example, can the sale object retrieve the price and quantities of the individual items in your design? For this, it's important to look at the different forms of information. And there are several ways in which a class A can have access to information in a class B. First, B could be an attribute of A. For example, a sale has a tax calculator object that it can access to compute taxes. B could also be a parameter of a method of A. For example, a sale has a compute total method that gets a tax calculator object as a parameter. Another way to do it is that B is a local object in a method of A. Whenever sale calculates the total, it first creates a tax calculator object in the method. And finally, there is global visibility. There is a global variable that contains a tax calculator object somewhere that everybody uses. When you validate your design, you can run through each of the use cases and ask yourself the question: is the information that we need for this use case visible, and how? To conclude, in object-oriented design, we think of objects as managers of responsibilities. We can use Larman's grasp principles to help us assign responsibilities to the concepts in our domain model. This helps us move from a conceptual domain model to a specification of objects and responsibilities, leading to a concrete design. This is the end of the video about object-oriented design. Please pose any questions you have in the Teams channel of this course. Thanks for watching, and catch you in the next one.